Okay, let's unpack this. Have you ever truly stopped to wonder how these seemingly magical feats of artificial intelligence, like machines learning to see, understanding human language, or even, predicting your next favorite song, actually work behind the scenes?
It's fascinating stuff, isn't it?
It really is. It all boils down to deciphering the intricate, often hidden language of data. Today we're embarking on a deep dive into the fundamental building blocks and sophisticated techniques that empower us to make sense of truly vast amounts of information, extract those elusive hidden patterns, and ultimately, well, build the intelligence systems that are reshaping our world.
Yeah.
It's a journey from the elegant simplicity of basic vector math all the way to the complex algorithms that are fueling the current AI revolution.
And what's truly fascinating here and what we'll explore is exactly how these seemingly abstract mathematical concepts don't just exist in theory. They translate directly into practical, tangible tools that fundamentally shape our digital world every single day. We'll start with the very core ideas. How we represent data in a way machines can understand, then how we uncover its intrinsic structure and hidden relationships. And finally, how we leverage that profound understanding to make powerful predictions, group similar items together, or accurately classify new incoming observations.
So let's start at the very bedrock with what often feels like the most fundamental unit of data when we're dealing with these intelligent systems, the vector.
The vector, yes.
Foundational. When we talk about data living in a multidimensional space, whether it's 2 dimensions or thousands, a single data point is essentially represented as a vector. It possesses both a direction and a magnitude. But how do we actually quantify its size or its length in this abstract multidimensional realm? It's not like we can pull out a ruler, right?
That's a perfect place to begin because understanding the size of a data point or, the distance between points is foundational to nearly everything else we do. The length or magnitude of a vector, let's just call it video, regardless of whether it resides in a simple two-dimensional plane or a complex non-dimensional space. It's calculated using a principle very similar to the Pythagorean theorem you might remember from high school geometry.
Ah, okay. So it connects back to that.
It does, yeah. Instead of just two sides of a right triangle, you consider each of its individual components or features. You square each of those components, sum all those squared values together, and then you take the square root of that sum.
Right.
So if your vector has components v dollars, v2, dots, vn, its magnitude, often written as a vex, it's exactly that. Square t v12 plus v22 plus dots plus vn2.
Got it.
This single number provides a quantifiable measure of that data point's extent or strength in its feature space, and it becomes incredibly important for things like understanding distances and relationships within our vast data sets.
So it's really the multidimensional version of finding the hypotenuse that clarifies it a lot.
Exactly. You got it.
Now, let's take a step further with this geometric thinking. Imagine you have a vast cloud of data points scattered throughout this multidimensional space. Maybe customer purchasing habits or genetic markers, each a complex vector. For various reasons, you might want to simplify this data, perhaps by projecting all those complex points onto a single line, or maybe a lower dimensional plane. Why would we even consider doing this, and how do we ensure that when we do, we're getting the best possible representation, minimizing any loss of crucial information?
That raises a critical question. What exactly does best signify in this context? Geometrically speaking, the best way to represent a point vec onto a line, and we can represent that line with another vector, say a vec is achieved when the error vector is perfectly perpendicular to that line.
Perpendicular, okay.
Think of it like dropping a plumb line from your point straight down to the line. The error vector, let's call it vec of vec, is simply the difference between your original data point, vecag, and its new simplified representation, or proxy, vec on that line. So vecac, vecac.
Right. When this error vector is orthogonal or perpendicular to the line, it means we have minimized what we call the reconstruction error. This error is quantified as the square of the length of that error vector. The error vector isn't perpendicular, well then the reconstruction error isn't at its minimum and you haven't found the most faithful, simplified representation.
So we're striving for the shortest possible distance from the point to the line, essentially.
Yeah.
And this applies even if we can't visually perceive that perpendicularity in, say, a 50-dimensional space. It's still mathematically true.
Precisely. That's the beauty of linear algebra. These geometric concepts extend seamlessly into any number of dimensions, even if our human minds, struggle to visualize them beyond 3D.
Right.
The mathematical principle holds true for any null or dimensional vectors. The formula for the projection of a vector vec_dal onto a unit vector, vec_ep neatly represents a line passing through the origin, is given by vec_dal.
Okay, the dot product is involved there. Yes, the dot product, VF2, is just a scalar number. It tells us how much of defect lies in the direction of vectus. So while you can't literally see a perpendicular line in a 30-dimensional space, the underlying mathematical principles, like the dot product, still perfectly define these geometric relationships and allow us to effectively simplify complex data while retaining as much essential information as possible.
That's a truly powerful abstraction. Okay, so if we have a data set with many, many features, maybe hundreds of attributes for each customer, or thousands of genes in a biological sample, how do we, without manually trying every single possible line, find these best lines or directions that capture the most information, the most variance in our data? It sounds like a problem perfectly suited for an algorithm to uncover.
This is exactly where principal component analysis, or PCA, really steps onto the stage.
Ah, PCA. Heard a lot about it.
It's a cornerstone technique, primarily employed for dimensionality reduction. The fundamental idea is to transform your high-dimensional data into a new, lower-dimensional coordinate system. The new axes in this system are called principal components.
Okay.
What makes them special is that they are uncorrelated with each other, and they're ordered by how much variance they explain in your data. The first principal component captures the most variance, the second captures the next most, and so on.
Like finding the main themes.
Exactly. It's akin to finding the main strengths or themes in your data.
So it's essentially hunting for the directions where our data shows the greatest spread or variability. How does the algorithm mathematically determine these most informative directions? What's the mechanism?
PCA relies heavily on something called the covariance matrix, often represented by dollar.
Covariance matrix.
Right. Imagine a grid or a table where each entry tells you how much one feature in your data varies together with another feature. For a data set that's been mean-centered, meaning we've adjusted all the data points so their average is at the origin, the covariance matrix is always perfectly symmetrical.
Symmetrical, okay.
Mathematically, for a data set of dollar data points, it's typically defined as frash1 n felu t dollar. Or, if you were to arrange your data points as columns in a matrix XD dollar, then Wella dollars can be more compactly expressed as frash1n and XD dollar. This matrix is essentially a map of all the interfeature relationships and variability within your data.
A map of relationships, I like that. And once we've built this intricate map, this covariance matrix, how do we then extract the principal components themselves from it? What's the key step?
The principal components are actually the eigenvectors of this covariance matrix.
Eigenvectors. Okay, bringing back some linear algebra memories.
Exactly. Now, if you're not deeply immersed in linear algebra, you can think of eigenvectors as the natural axes or fundamental directions of variance within your data. Each eigenvector represents a specific direction along which your data is most spread out, and its corresponding eigenvalue. That's simply a numerical measure of how much variance or spread there is along that particular eigenvector direction. So the eigenvector with the largest eigenvalue will give you the first principal component, which captures the most significant variance in your data.
Largest eigenvalue, most variance. Got it.
To illustrate this, imagine you calculate the eigenvalues for a data set and they turn out to be 7, 5, and 1.
Okay.
The total variance across all dimensions would be the sum of these eigenvalues, which is 13. The first principal component with an eigenvalue of 7 alone would explain 713 times $100, which is approximately 53.84% of that total variance.
Well, over half.
Right. By choosing to keep only the principal components associated with the largest eigenvalues, you efficiently reduce the dimensionality of your data while preserving the most vital information, almost like finding the core narrative in a sprawling story.
That's a truly elegant way to quantify importance and prune away the noise. But what about that reconstruction error we discussed earlier? If we reduce the dimensions of our data using PCA, are we always, by definition, losing some information, even if it's minimal?
Not necessarily. This is a fantastic point, and it highlights a crucial insight of PCA. If your data set inherently lives in a lower dimensional subspace,
Meaning?
imagine you have 2,000 data points, each described by 30 different features, so they initially reside in a 30-dimensional space. But what if all those 2,000 points actually fall perfectly within a 4-dimensional subspace inside that larger 30-dimensional space?
Okay, like they're really only defined by 4 key things.
Exactly. Perhaps they represent something truly 4-dimensional, but they were collected with redundant or highly correlated measurements. In such a scenario, if you use PCA to identify and retain only the principal components that span that intrinsic four-dimensional subspace, you would achieve zero reconstruction error.
Zero, really?
Zero. No information is lost because you're simply uncovering the true lower dimensional manifold where your data genuinely resides. It's like having a crumpled piece of paper in a 3D room. PCA helps you flatten it out and realize it's fundamentally a 2D object.
So the variance captured by a principal component is directly linked to how well the data points project onto it. Could you elaborate on how we might calculate that variance from those projections themselves? It feels like a very direct, intuitive connection.
It is indeed a direct connection. The variance along a specific principal component can be calculated directly from the squared lengths of the projections of your data points onto that component.
Ah, okay.
Let's take a simplified example to make it concrete. Imagine you have 6 data points, and after projecting them onto the first principal component, the lengths of these projections are 8, 7, 3, 5, 2, and 4.
Right.
To calculate the variance along that component, you simply sum the squares of these projection lengths and then divide by the number of points. In this case, it would be $82 plus 72 plus 32 plus 52 plus 22 plus 42, $6.
Okay, do the math.
That works out to $64 plus 49 plus 9 plus 25 plus 4 plus 16, $6, which equals $167. $6, roughly $27.83. This strong, direct relationship between how far your data spreads along a principal component and the variance it explains is one of the most powerful and insightful aspects of PCA.
Once we understand how to represent data and even reduce its dimensions to their most essential components, the next natural, often ultimate step is to predict something.
Prediction, yes. The holy grail for many applications.
Whether it's the future price of a house, tomorrow's temperature, or the likelihood of a customer clicking on an ad, this brings us squarely into the powerful realm of regression. How exactly do we go about fitting models to data in this context? And perhaps even more importantly, what does it truly mean for a predictive model to be considered good?
At its core, linear regression aims to uncover and quantify a linear relationship between a set of input features and a continuous target variable. Our goal is to essentially draw the best fit line, or in higher dimensions, a hyperplane, through our data points, capturing this relationship.
The best fit line.
And the goodness of such a model isn't subjective. It's precisely quantified by how closely its predictions align with the actual observed values. This alignment, or lack thereof, is typically measured using what we call a loss function or error function, which our algorithms then strive to minimize.
So the model form is usually a linear equation, something like y equals w dollars plus w1 by 1 bow, where dollars is the intercept and w dollars is the slope, much like what we learned in basic algebra.
That's the simplest expression for a single feature. For datasets with multiple features, it seamlessly extends to y equals w dollars plus w1 by 1 plus w2 by 2 plus dots plus wn xn dollar.
Right, just add more terms.
Exactly. Now, when we talk about those loss functions, the most prevalent one, by far, is the squared error, often appearing as mean squared error, MSE, or sum of squared errors, SSE.
Yeah, I hear that one a lot.
It calculates the sum of the squared differences between each actual value and its corresponding predicted value. So it's a text loss summed of errors. Minimizing this particular loss function implicitly assumes that the noise or random errors in your data follow a Gaussian or normal distribution.
Okay, so the choice of loss function has assumptions baked in. Are there other significant types of loss functions used in regression, perhaps for different types of data or assumptions?
Indeed. Another notable one is the absolute error. This loss function sums the absolute differences between actual and predicted values.
Absolute difference, not squared.
Right. It's particularly useful when the noise in your data doesn't necessarily follow a Gaussian distribution, but perhaps something like a Laplace distribution, where the probability of an error decreases exponentially with its magnitude.
Okay.
In such cases, minimizing the absolute error is actually the maximum likelihood approach. A key takeaway here is its robustness to outliers. Because it penalizes large errors linearly rather than quadratically, it's less sensitive to extreme data points that might skew the model if squared error were used.
So it doesn't freak out as much about outliers. That's useful.
Very useful in noisy real-world data.
So once we've decided on our loss function, how does the model actually go about finding the specific weights, the w dollars, w11, and so on, that minimize this chosen error? Is there a direct once-and-for-all solution?
For standard linear regression with squared error, yes, there is. The optimal weight vector required can be calculated directly using what are known as the normal equations.
Right.
DAPZT, XDC, BXDVs. Yes, it involves matrix inversion and multiplication, but this formula, derived from calculus, gives you the exact set of weights that yield the absolute minimum squared error for your given input data matrix, $6, and target labels of $80. It's a closed-form solution, meaning you don't need to iterate to find the answer. Compute it once, and you're done.
And when we visualize this error in linear regression, what exactly are we looking at? Is it the same perpendicular distance we discussed when talking about PCA and projections?
This is a really crucial distinction and one that often causes confusion, so it's good you brought it up.
Okay.
In linear regression, the residuals, which are our errors, are almost universally measured as the vertical distances from each data point to the regression line.
Vertical distances.
Yes, we are minimizing the sum of these vertical squared distances. Think about it. You're predicting a value given in $6, so the error is naturally measured along the y-axis. This is distinctly different from PCA.
Right, where it was perpendicular.
Exactly. In PCA, as we discussed, the errors are defined as the perpendicular distances from the data points to the principal components. In PCA, you're trying to find a line that captures the most spread by minimizing the orthogonal distance to that line. While in linear regression, you're explicitly predicting one variable based on others, and thus you minimize the error in that prediction. Different goals, different error measures.
That makes a lot of sense, grounding the error calculation in the problem itself. So we have these powerful tools to fit lines, but what if our chosen model isn't complex enough to capture the true underlying relationship in the data? Or conversely, what if it's too complex and starts picking up on noise? This sounds like the classic bias-variance trade-off.
You've hit on one of the most fundamental dilemmas in machine learning. This trade-off is omnipresent.
It always comes up.
It does. Simple models, for instance. A straight linear regression line applied to data that clearly have a curvy nonlinear relationship tend to underfit.
Underfit. Too simple.
Exactly. This means they have high bias. They make strong, incorrect assumptions about the form of the relationship, consistently missing the true pattern. However, they usually have low variance because they aren't sensitive to minor fluctuations or specific data points in your training set. They're too rigid.
Okay.
On the other end of the spectrum, highly complex models, such as a high-degree polynomial regression or a very deep decision tree, tend to overfit.
Overfit. Too complex.
Right. These models have very low bias on the training data because they're flexible enough to capture almost every detail, including the random noise. But this flexibility comes at a cost. Very high variance. They essentially memorize the training examples rather than learning the underlying generalizable patterns.
They fail on new data.
Precisely. Consequently, they perform poorly on new, unseen data because they react wildly to even slight differences. It's a constant balancing act between being too simple and too complex.
That's a great way to put it, a constant balancing act. Sometimes solving for those optimal weights directly using the normal equations isn't feasible, maybe especially with truly enormous data sets, or when the model becomes much more intricate. What's our strategy then?
In those prevalent scenarios, we pivot to iterative optimization algorithms with gradient descent, GD, and stochastic gradient descent, SGD, being the champions.
GD and SGD.
Okay.
Instead of single direct calculation, these algorithms embark on a journey. They start with an initial guess for weights, then they iteratively adjust those weights by taking small steps. The direction of each step is precisely chosen to reduce the loss function as rapidly as possible.
Going downhill on the error landscape.
Exactly. Gradient descent computes this optimal step direction by calculating the slope of the loss function over the entire data set for each single update. This can be computationally prohibitive for massive data sets.
Right, using all the data every time sounds slow. It can be very slow. Stochastic gradient descent, or SGD, offers a more scalable, albeit somewhat noisier, alternative. SGD updates the weights based on the gradient computed from just a single data point or a small batch of data points at a time.
Just one or a few.
Yeah. This makes it significantly faster for large data sets, though its path to convergence can be more erratic, like navigating a mountain path in a fog. It jumps around a bit more.
So how big should these steps be as the algorithm descends this loss function landscape? Is there a critical parameter that dictates this? It sounds important.
Absolutely, and it's perhaps the most crucial hyperparameter in gradient-based optimization, the learning rate, typically denoted by alpha.
Alpha, okay.
This parameter dictates the size of each step taken in the direction of the negative gradient. The learning rate is a Goldilocks parameter. If it's set too high, the algorithm might repeatedly overshoot the minimum, oscillating wildly and never settling, or even diverging completely, causing your loss to explode instead of decrease.
Like taking giant leaps down a hill and tripping.
Exactly. Conversely, if the learning rate is too low, the algorithm will inch its way towards the minimum at an agonizingly slow pace, taking an impractically long time to converge to the optimal weights. Finding the right learning rate is often a delicate art, involving careful tuning and sometimes employing sophisticated techniques like learning rate schedules that gradually decrease alpha over time.
Finding that just right value. And speaking of SGD, if it's updating weights with each batch or even each individual data point, what's ultimately considered the final weight vector after multiple iterations? Does it just pick the last one?
That's a good point. Since SGD's path is noisy, the last weight vector might not be the best representation. A common and effective practice for the final weight in SGD, especially to account for the inherent noise in its updates, is to take the average of all the weight vectors updated across all the iterations.
Averaging them smooths things out.
Exactly. This averaging effect helps to smooth out the noisy individual updates and provides a more stable, robust estimate of the optimal weights, often leading to better generalization performance than just taking the very last weight vector.
Okay, linear regression is powerful for linear relationships, but the world, and certainly data, often isn't linear at all. We can't just draw a straight line through a curving trend and expect good results. What then?
That's precisely where kernel regression steps in as a clever solution. This powerful technique allows us to model highly nonlinear relationships without explicitly transforming our data into a higher dimensional space.
The kernel trick again.
Or related.
Very related. The kernel trick, which we'll delve into more deeply when we discuss support vector machines, implicitly maps our original data into a potentially much higher dimensional feature space where, surprisingly, the relationship between features and target might actually become linearly separable or linearly predictable. So it pretends it's linear in a higher dimension.
In a sense, yes. Once that implicit mapping is done, we can apply what are essentially linear regression principles in that higher dimension. The magic is that the resulting model, when viewed back in our original data space, accurately captures the intricate, curvy, nonlinear patterns.
Cool. What kinds of kernels do people use?
For example, using polynomial kernels, say of degree 2 or 3, allows us to fit quadratic or cubic curves. And Gaussian, or radial basis function, RBF, kernels are incredibly versatile, capable of capturing highly complex, even infinitely nonlinear relationships.
That sounds like a powerful computational sleight of hand to tackle nonlinearity. Now let's circle back to our overfitting problem, which is a constant nemesis in machine learning.
Always lurking.
How do we build models that are not just complex enough to capture patterns, but also generalize effectively to new, unseen data, especially when we're dealing with potentially very intricate relationships?
Here's where it gets really interesting. This is where regularization techniques make their grand entrance. They are specifically designed to prevent overfitting by introducing a penalty term into the model's loss function.
A penalty.
For what? A penalty that actively discourages the model from assigning excessively large or wild weights to features, thereby subtly pushing the model towards simpler, more parsimonious solutions that tend to generalize much better to new data. It's like putting a speed limit on how much influence any single feature can have.
So it's like putting a leash on the model's enthusiasm to fit every single training point perfectly. What are the main types of regularization we commonly use?
Exactly. It's about reining in that enthusiasm. The two most common and impactful forms are ridge regression and lasso regression.
Ridge and lasso.
Ridge regression, also known as L2 regularization, modifies the squared error loss function by adding a term. Here, val is the squared Euclidean norm of the weight vector, essentially the sum of the squares of all the weights.
Squaring the weight.
Yes. By adding this penalty, ridge regression heavily penalizes large coefficients, subtly shrinking them closer to zero. Importantly, it drives them towards zero, but very rarely exactly to zero.
Almost zero, but not quite.
Right. The regularization parameter lambda is crucial. As lambda increases, the penalty becomes stronger, weights shrink more aggressively, and the model becomes simpler. If lambda is set too high, the model might become too simple and start underfitting. Conversely, if lambda approaches zero, ridge regression effectively reverts to standard linear regression.
So lambda controls the strength of the leash.
Perfectly put, and a key insight for ridge. If multiple different weight vectors could produce the same training error, ridge regression will always prefer the one with the smallest squared length, promoting a more stable and less spiky solution.
And how does lasso regression, or L1 regularization, differ from ridge? Does it also just shrink coefficients?
Lasso regression, or L1 regularization, takes a slightly different approach. It adds lambda vec1 to the loss function, where del1 is the L1 norm, the sum of the absolute values of the weights.
Absolute values, not squares.
Correct. The crucial distinct feature here is that the L1 penalty has a tendency to drive some weights exactly to zero.
Exactly zero. Interesting.
Yes. This leads to what we call sparse solutions. What's remarkable about this is that it effectively performs automatic feature selection. Features whose weights are driven to zero are entirely excluded from the model, making the model not only simpler but also potentially more interpretable, as it tells you which features it considers irrelevant.
Wow, so it actually zeroes out features it thinks aren't useful.
Exactly. This can be incredibly powerful when you're dealing with data sets that have a very large number of features, many of which might be redundant or irrelevant. Lasso helps you find the truly important ones.
That's truly powerful, having the model itself prune away irrelevant features. But with all these choices, like different levels of model complexity and crucial regularization parameters like lambda to tune, how do we actually go about choosing the best model or the optimal level of regularization that will generalize well to the real world? How do we pick lambda?
This is where cross-validation becomes absolutely indispensable. It's a robust and widely used technique that helps us rigorously assess how well a model will truly generalize to unseen data.
Okay, cross-validation.
And it's paramount for selecting the optimal hyperparameters that govern a model's behavior, such as the lambda value in ridge or lasso, or the degree of a polynomial kernel. It's our best defense against over-optimizing for our training data.
So how does this method work in practice? Does it involve repeatedly splitting our data?
Precisely. The most common and widely adopted form is k-fold cross-validation. The process is elegant. You first divide your entire dataset into what we call equally sized folds or segments.
K-folds, like pieces of the data.
Exactly. Then, in a series of iterations, you systematically use one of these folds for validation, testing your model's performance, and the remaining k-1 folds for training your model.
Train on K1, test on 1.
Yes. This procedure is repeated $1 times, ensuring that each and every fold serves as the validation set exactly once. For example, in three-fold cross-validation, your data is partitioned into 3 parts. In the first iteration, parts 1 and 2 are used to train the model, and part 3 is used for validation. In the second, parts 1 and 3 train, part 2 validates, and so on.
And then you average the results.
Exactly. The performance metrics, like mean, squared error, or accuracy from each of these dollar iterations, are then averaged to yield a much more reliable and less biased estimate of the model's true generalization ability.
And I've heard of leave one out cross-validation, or LOOCV. Is that just an extreme version of K-fold? Sounds intense.
It is indeed a special, very intensive case. Leave one out, cross-validation, or LOOCV, is essentially K-fold, where LO dollars is set equal to none dollar, the total number of data points in your dataset.
K equals N.
Wow. So, in each iteration, you train your model on none data points and validate it on the single remaining data point. This means you end up training none distinct models.
N models. That sounds computationally expensive.
It can be prohibitively expensive for large data sets. While LOOCV provides an extremely accurate and almost unbiased estimate of generalization error because it uses nearly all data for training in each fold, its computational cost makes it less practical for many real-world applications. 5-fold or 10-fold are much more common.
Okay, shifting gears now from predicting continuous numbers to predicting discrete categories. What class does this email belong to? Is this image a cat or a dog? This is the fascinating realm of classification. Let's begin with some foundational approaches for categorizing the world.
Right. Linear classifiers, at their heart, operate by drawing a decision boundary in the feature space. Imagine this boundary as a simple line in 2 dimensions, a flat plane in 3 dimensions, or a hyperplane in higher dimensions.
A dividing line.
Exactly. The fundamental principle is straightforward. Data points falling on one side of this boundary are assigned to one class, while points on the other side are assigned to another. These models are widely popular due to their inherent simplicity and ease of interpretation.
And where do we typically start when exploring these linear classifiers? What's a classic example?
We often begin our journey with the perceptron algorithm.
The perceptron. Okay.
Its decision boundary is mathematically defined by the equation vec0, 0 day, where vec is the weight vector that defines the orientation of this boundary. This creates a hyperplane that effectively divides the Noether-dimensional feature space into two distinct regions, each corresponding to a different class. The perceptron is notably an online learning algorithm.
Online, meaning it learns as data comes in.
Yes, meaning it doesn't process all data at once. Instead, it updates its weights incrementally as it encounters new data points one by one or in small batches.
How does the perceptron actually learn this boundary? What's its core learning mechanism, its update rule?
The update rule for the perceptron is remarkably simple and elegant. If a data point vecchia day with its true label y day dollar is misclassified, meaning its predicted sign, based on vecchia day, doesn't match its true label, or more precisely, if vecchi t vecchi d is 0...
So if it gets it wrong.
Exactly. If it gets it wrong, then the weight vector vecchi is updated. The update rule is vecchia day plus uag. You just add or subtract the misclassified points vector, scaled by its label, to the weight vector.
Simple addition, subtraction.
Yeah. The algorithm continues to cycle through the training data, applying this update whenever a mistake is made, until all points are correctly classified or a maximum number of iterations is reached.
So if the data is truly separable, like if a line can separate the classes, it's guaranteed to find a perfect boundary. And do we have any idea how many mistakes it might make before it gets there?
For linearly separable data, meaning a perfectly straight line or flat plane can indeed separate the classes, the perceptron algorithm is famously guaranteed to converge. It will eventually find such a separating hyperplane.
Guaranteed convergence. Nice.
What's even more insightful is that the maximum number of mistakes it can make during its entire training process is theoretically bounded. This bound is given by R2 gamma tar, where dollar represents the maximum norm or length of any data point in your dataset, and gamma dollar is the margin of the optimal linear separator.
Okay, so there's a limit on its mistakes.
Yes, this bound gives us a theoretical understanding of its efficiency and convergence properties.
That's a fascinating theoretical guarantee. But does anything practical affect its behavior, like the order in which you feed it the data points? Does that matter?
Yes, that's one of its interesting practical quirks. While convergence is indeed guaranteed for linearly separable data, the order in which you present the data points to the algorithm for updates can absolutely influence the specific final weight vector that the algorithm converges to.
So different order, potentially different line.
Potentially, yes. Different sequences can lead to different but equally valid separating hyperplanes. It's also critical to remember that the perceptron algorithm is not robust to outliers. Its guarantee of convergence strictly holds only in the linearly separable case.
What happens if it's not separable?
If your data isn't perfectly separable, perhaps due to noise or overlapping classes, the perceptron might not converge at all, or it could simply oscillate indefinitely without finding a stable solution.
Okay, so it needs clean separation. The perceptron gives us a hard classification. It's either class A or class B. No, maybe. But what if we want something more nuanced, like probabilities or a measure of confidence in its prediction? We need to know not just what it predicts, but how sure it is.
That's precisely where logistic regression makes a crucial advancement. Unlike the perceptron, logistic regression provides a probabilistic output, a value ranging precisely between 0 and 1, which can be interpreted as the probability of a data point belonging to a particular class.
Probability between 0 and 1.
It achieves this by taking the score, which is a simple linear combination of features and weights, much like in the perceptron, and then transforming this score using the sigmoid or logistic function. This function, frac11 plus e.
That S-shaped curve.
Exactly, the S-shaped curve. It effectively squashes any real-valued input score into the 0-1 range, making it interpretable as a probability.
So even though it's giving us a probability, does it still maintain a linear decision boundary underneath? Is the dividing line still straight?
It does. The underlying decision boundary for logistic regression remains linear, defined by v by t, vecui m2, just like the perceptron. What changes is how we interpret the output.
Okay.
For instance, a probability greater than 0.5 might be assigned to class 1 and less than 0.5 to class 0. However, the specific threshold of 0.5 isn't set in stone. You can adjust this threshold to fine-tune the model's behavior, allowing for critical trade-offs between false positives and false negatives.
So you can slide the threshold.
Yes. For example, in a medical diagnosis scenario where missing a positive case is far worse than a false alarm, you might set a very low probability threshold, say 0.1, to maximize detection, even if it increases the number of false alerts.
Makes sense. And how does logistic regression express its confidence or certainty in a prediction?
The farther a data point's linear score, The GoT-vex is from the decision boundary, where VT-vec E, the closer its probability output by the sigmoid function will be to either 0 or 1.
Further away means more sure.
Exactly. This means the model is more confident in its prediction for that particular data point. For example, a point with a score of 10 will yield a probability very close to, indicating high confidence in that class, whereas a point with a score of 0.1 will result in a probability just slightly above 0.5, reflecting much less certainty.
Then how is it trained? What's the loss function?
The training process for a logistic regression aims to optimize a loss function. Specifically, it uses the logistic loss function, which aims to maximize the log likelihood of the observed data. This effectively means it's trying to find the set of weights that make the actual observed outcomes as probable as possible given the model.
We've now covered the basics of linear models for both predicting numbers with regression and categorizing data with classification. But the real world is rarely just about straight lines and simple divisions. What if our data relationships are much more complex and nonlinear? Or what if we want to leverage sophisticated probabilistic reasoning explicitly? We need to move beyond simple lines and hyperplanes to truly capture the nuances of reality.
This is where we truly elevate our game. Here, we'll dive into advanced methods that are capable of creating far more intricate, curvilinear decision boundaries, or that explicitly model the underlying statistical distributions of the data. These techniques offer immensely greater flexibility and power for tackling the most complex real-world challenges.
Let's start with decision trees. They seem almost intuitively easy to understand, like a series of if-then-else rules or a flowchart for making decisions. How do they actually work at a high level?
Decision trees are remarkably intuitive and powerful. At their core, they operate by recursively partitioning the feature space into distinct rectangular regions.
Rectangular regions.
Yes. Imagine it like asking a series of binary yes or no questions about your features at each node of the tree. For example, is the customer's age greater than 30? Or is the income less than $50,000? Each question corresponds to a threshold on a specific feature.
Like a flowchart.
Exactly like a flowchart. You follow the answers down the branches, moving from one node to the next, until you finally reach a leaf node. Each leaf node then gives you a concrete class prediction or a numerical value for regression. This process effectively carves up your data space into non-overlapping boxes, with every data point within a specific box being assigned the same class label.
So how does the tree intelligently decide which question to ask or where to make a split at each step? It must be trying to optimize something, right, to make the best split.
Precisely. The critical challenge in building a decision tree is to choose splits that maximize information gain or minimize impurity at each node.
Impurity, like how mixed up the classes are.
Exactly. One of the most common measures of impurity is entropy. Entropy quantifies the randomness or mixed-upness of the class labels within a particular node. To put it simply, if a node contains an equal mix of classes, its entropy is high. If it contains mostly one class, its entropy is low.
Low entropy is good, more pure.
Yes. For binary classification, if powers is the proportion of points belonging to class 1 in a node, its entropy is entropy 1p. A perfectly pure leaf node, where all points belong to the same class, will have an entropy of 0. The goal is to find splits that significantly reduce this impurity, making the child nodes as pure as possible.
And how do we quantify that information gain then, based on this reduction in impurity or entropy?
Information gain is a direct measure of the reduction in entropy achieved by a particular split. You calculate the entropy of the parent node before the split.
Okay.
Then you subtract the weighted average of the entropies of its child nodes after the split. The formula is fras parent left ta, where left and right represent the number of data points that go into the left and right child nodes, respectively.
So biggest drop in entropy wins.
Essentially, yes. The algorithm will evaluate many possible splits at each node and typically chooses the split that yields the highest information gain, ensuring the most effective partitioning of the data at that step.
It sounds like a decision tree can grow very complex very quickly, with many, many layers of decisions. Are there specific problems that arise from allowing a tree to become too deep or too intricate?
Indeed. Deep decision trees are notoriously prone to overfitting, a concept we discussed earlier.
Back to overfitting again.
It's a recurring theme. If allowed to grow unchecked, they can create highly specific, intricate rules that perfectly fit the training data, down to capturing every tiny piece of random noise and outlier. This often leads to a zero misclassification error on the training set, which looks great on paper, but results in very poor generalization to new, unseen data.
Memorizing the noise.
Precisely. It's like building a highly specialized house for one specific family, which then becomes unusable for anyone else. And a surprising fact about their complexity. To form even a simple bounded region in a single dimension, for instance, to classify all points between 0 and 1 on a number line, a decision tree needs at least a depth of 2.
Depth 2, just for an interval. Wow.
Yeah, you need one split for greater than 0 and another for less than 1. This illustrates how quickly complexity can escalate and why pruning or limiting the depth of trees is a crucial step in practice.
Moving on, can we leverage probabilities directly to classify, perhaps by making some simplifying assumptions about how our features relate to each other, using probability theory more directly?
Absolutely. This is the domain of the naive Bayes classifier. It's a probabilistic classifier that elegantly leverages Bayes' theorem for classification.
Bayes' theorem.
Okay. The naive part comes from its crucial simplifying assumption. It assumes that all features are conditionally independent of each other, given the class label.
Conditionally independent. What does that mean in practice?
For example, if you're classifying spam, naive Bayes would assume that the probability of seeing the word Viagra is independent of seeing the word free once you know whether the email is spam or not.
Even though they might often appear together in spam.
Exactly. This assumption is often not perfectly true in reality, but it dramatically simplifies the estimation of parameters and makes the model incredibly computationally efficient, especially for high-dimensional data where explicitly modeling all feature dependencies would be intractable.
So if this conditional independence assumption holds, what does that mean for the number of parameters we need to estimate to make the model work? How much simpler is it?
It makes an enormous difference. For binary features, where a feature is either 0 or 1, and with the class conditional independence assumed, the number of free parameters you need to estimate is relatively small. $2 times d plus all 1, where dollars is the number of features.
Okay, linear in the number of features.
Yes, you effectively need a probability for each feature given each class, plus the prior probabilities of the classes themselves. If, however, this conditional independence assumption is not made, if you have to model every possible interaction between features, the number of parameters explodes exponentially to $2 times 2d1 plus auto 1.
Exponentially. Okay, that's a huge difference.
It's a massive difference. This drastic difference in parameter count is why the naive assumption is so powerful for scalability and why naive Bayes can handle very high-dimensional data where other models might struggle due to computational complexity.
And what kind of decision boundary does a naive Bayes classifier produce? Is it always linear, like the perceptron or logistic regression?
Not necessarily, and this is a subtle but important point. The decision boundary for naive Bayes can be linear or nonlinear, and its shape depends entirely on the underlying distributions of your features.
Depends on the feature distributions.
Exactly. For example, if your features are continuous and assumed to be Gaussian distributed, the decision boundary will be linear if the variances of the features are equal across the different classes. However, if those variances differ between classes, the decision boundary will become nonlinear, often taking a quadratic or even more complex form.
So it can be curved, too.
It can. This flexibility allows naive Bayes to handle more intricate data distributions than strictly linear classifiers. A classic practical application is email spam classification, where the presence or absence of certain words, features, is used to calculate the conditional probabilities, which then combine using Bayes' rule to predict the overall likelihood of an email being spam.
Now let's talk about support vector machines, or SVMs. These always sound quite powerful. If we're looking for the best possible linear separator, one that provides the clearest, most robust distinction between classes, how do SVMs achieve that compared to, say, a perceptron, which just finds any separating line?
Here's where it gets really interesting. SVMs operate on a fundamentally different principle. They aim to find the hyperplane that maximizes the margin.
Maximize the margin. What's the margin exactly?
The margin is the distance between the decision boundary and the closest training data points of any class. These closest points are critically important and are called support vectors because they are the ones that fundamentally define or support the position and orientation of the separating hyperplane.
So the points right on the edge dictate the boundary.
Precisely. The intuition behind maximizing this margin is that a wider margin leads to better generalization performance. It creates a more robust and less susceptible separation between classes, allowing the model to handle new, slightly varied data more effectively. It's like drawing the widest possible road between two towns.
So for data that can be perfectly separated by a line, it's about finding the widest possible buffer zone between the classes.
Exactly. For linearly separable datasets, the hard margin SVM seeks out the separating hyperplane that achieves the largest possible margin. The support vectors in this specific case are the training points that lie precisely on the supporting hyperplanes, which are parallel to the decision boundary and are defined by v-vios plus bpm1.
Okay.
A key mathematical insight here is that the weight vector, v-var, of this optimal separator will have the smallest norm, v-var. This inverse relationship means that minimizing the v-val directly maximizes the margin.
Smallest norm equals widest margin.
Yeah.
Interesting.
Yes. And the actual width of this separation, this optimal buffer zone, is then calculated as veikvaluable.
But what happens in the real world when data isn't perfectly linearly separable? There are always some outliers or some overlap that prevents a clean, straight-line separation. SVMs can handle that.
That's a very common real-world scenario, and it's expertly handled by the soft margin SVM. This formulation introduces what are called slack variables, typically denoted as a finari, for each individual data point.
Slack variables, like giving some points some slack.
Exactly. These slack variables are brilliant. They allow for a controlled amount of misclassification or violation of the margin. The optimization problem then elegantly balances two objectives: minimizing the size of the weight vector, thereby maximizing the margin, and simultaneously minimizing the sum of these slack variables, thereby minimizing the penalty for misclassifications or margin violations.
Okay, so it's the trade-off.
It is. The objective function for a soft margin SVM becomes frec1 plus c sum day.
So these tie values are like a quantifiable penalty for points that don't play nicely with the ideal separation, how much they mess things up.
Precisely. A data point that violates the margin or is outright misclassified incurs a penalty proportional to its Daliao. The magnitude of die for any given point is calculated as max, 1 yi plus b.
Okay.
This means if a point is correctly classified and lies comfortably outside the margin, its TDAL value is 0, and it contributes no penalty. But if it creeps inside the margin, or worse, ends up on the wrong side of the decision boundary, its DDAL value increases proportionally to how badly it violates that ideal separation.
And what's the c in that equation? 2-1 plus c sum?
That is an absolutely crucial regularization hyperparameter that you, as the model designer, must tune. It controls the trade-off. A small dollar value means you're putting less emphasis on penalizing misclassifications, encouraging a wider margin even if it leads to more training errors. You prioritize the wide road.
Okay, more tolerance for errors.
Right. Conversely, a large dollar value heavily penalizes misclassifications, leading to a narrower margin and a much stronger attempt to classify all training points correctly, which, as we know, can sometimes lead to overfitting. You prioritize fitting the data perfectly.
So C is like the budget for mistakes.
That's a great analogy.
And are the support vectors themselves still defined the same way in this soft margin scenario? Are they still just the points on the edge?
The concept of support vector still holds, but their definition expands slightly in the soft margin case. Here, support vectors are any points for which the corresponding dual variable alpha, which comes from the mathematical optimization, is greater than 0.
Okay, based on the math.
Yes. This encompasses not just the points that lie exactly on the margin, but also points that fall within the margin, and even those that are misclassified but still influence the boundary. These are the points that actively influence the position and orientation of the decision boundary, even if they aren't perfectly separated by it. They are the critical points that the SVM focuses on.
Okay, that makes perfect sense for linear boundaries, even with some messiness. But we keep running into the same wall. What if the data itself simply isn't linearly separable, even with some wiggle room, in its original feature space? Think of data points that form a circle within another circle. A straight line won't ever separate them. How does SVM handle that?
And this is where the truly ingenious kernel trick for SVMs comes into play. It's one of the most elegant and powerful ideas in machine learning.
The kernel trick again. It sounds like magic.
It feels a bit like magic sometimes. Instead of explicitly transforming your data into a potentially much higher dimensional feature space where it might become linearly separable, a transformation that could be computationally prohibitive or even infinite, the kernel trick allows SVMs to compute the necessary dot products between data points as if they were already in that higher dimension, but without ever actually performing the expensive, explicit transformation.
Computes the result without doing the work.
Essentially, yes. It leverages special kernel functions that calculate the similarity dot product in that high-dimensional space directly from the original data points. This enables SVMs to learn incredibly complex, nonlinear decision boundaries in your original feature space without you ever seeing or defining that higher dimensional space directly.
That does sound like magic. How do we know if a mathematical function is a valid kernel that can be used for this trick? Are there rules?
There are. A function call is considered a valid kernel if it satisfies two main properties. First, it must be symmetric, meaning cabale vero.
Symmetric.
A second, and crucially, it must correspond to an inner product, a dot product in some transformed feature space, which we denote as phi-ves. This ensures that the kernel function is genuinely measuring a form of similarity or relationship between data points in a way that maps them into a valid higher dimensional space.
What are some popular kernels?
Popular examples include polynomial kernels, like VVAVSB, the dollar is the degree of the polynomial, or the incredibly versatile Gaussian radial basis function RDF kernels, given by Bayer Press. Gaussian kernels are particularly powerful as they can implicitly map data into an infinite dimensional feature space, allowing for remarkably flexible decision boundaries.
Infinite dimensions. So even though the SVM finds a linear boundary in this abstract, higher dimensional transformed space, what does that mean for the actual shape of the decision boundary back in our original data space, the one we can actually visualize? Is it still linear?
No, not at all. It means the decision boundary, when projected back into your original feature space, can be wildly nonlinear.
Like what?
For example, a linear boundary in a transformed space could translate to a perfect circle, an ellipse, a hyperbola, or even a very complex wavy curve in your original 2D or 3D data. This is precisely how kernel SVMs achieve their impressive power to model very complex class separations that are impossible with simple linear boundaries.
Makes sense.
And a quick but important practical note, particularly for kernel PCA, which also uses this trick, it's generally best practice to apply the kernel function first and then center the resulting kernel matrix rather than attempting to center the original dataset first and then applying the kernel.
Kernel first, then center. Got it.
This ensures that the centering operation is correctly performed in the implicit high-dimensional feature space.
We've now covered a wide array of individual models, each with its own strengths and weaknesses, its own preferred kind of data, and its own way of solving problems. But what if we could take the collective wisdom and strengths of many such models and combine them to create something even more powerful, more robust, and significantly more accurate than any single model could achieve on its own? Combining models.
This is truly the essence of ensemble learner techniques. They are about aggregating or combining the predictions from multiple individual models, which we often call base learners or sometimes weak learners, to improve the overall performance, enhance stability, and drastically reduce errors.
The wisdom of the crowd approach.
Exactly. The underlying philosophy is beautifully simple. The wisdom of the crowd often outperforms any single expert, especially when those experts offer diverse perspectives. It's like assembling a dream team of specialized individual models.
What's one of the foundational ways to combine these individual models into a more powerful ensemble? Where do we start with ensembles?
One of the earliest and most widely used ensemble techniques is bagging, which is short for bootstrap aggregation.
Bagging, okay.
Its mechanism is quite elegant and straightforward. You start by creating multiple different bags, or bootstrapped samples, from your original dataset. This is done by sampling with replacement.
With replacement, meaning some data points might get picked multiple times.
Exactly. You draw a random data point, put it in your bag, and then put it back into the original pool so it can be drawn again. Each bag has the same number of data points as your original dataset, but because of sampling with replacement, some points might appear multiple times in a given bag, and some might not appear at all.
So each bag is slightly different.
Yes. Then you train an independent base learner on each of these unique bags. These base learners are often high-variance models, like very deep decision trees, which on their own are quite prone to overfitting.
So how does this process of bagging actually help? What's the core benefit of training many models on these slightly different subsets of data? Why does that work?
The primary benefit of bagging is that it significantly reduces variance.
Reduces variance. How?
By training multiple high-variance models on these slightly different bootstrapped subsets of the data, and then averaging their predictions for regression tasks, or taking a majority vote for classification tasks, the overall variance of the ensemble is drastically reduced.
Averaging cancels out the noise.
Pretty much, think of it this way. Each individual model might be unstable, making slightly different errors due to the specific data it saw. But when you average or vote across many such diverse models, those individual errors tend to cancel each other out, leading to a much more stable, robust, and generalizable final prediction.
Okay.
And a key practical advantage of bagging is that since each base model is trained completely independently on its own bag, the entire training process can be done in parallel, making it very efficient for large data sets and complex models.
Parallel training. Good for speed. And what about random forest? That sounds a very specific and popular type of bagging algorithm. Is it just bagging with trees?
It is, yes, but with a twist. Random forest is a powerful and extremely popular extension of bagging, specifically designed for decision trees. It incorporates the core idea of bagging training multiple trees on bootstrap samples, but it adds an additional crucial layer of randomness.
More randomness. Where?
At each step, when a decision tree within the forest is deciding how to split a node, it doesn't consider all available features. Instead, it only considers and evaluates a random subset of those features.
Only looks at some features for each split? Why add that extra layer of randomness? Wouldn't you want the tree to see all the features to find the absolute best split?
That's a great question, and it's counterintuitive but brilliant. The benefit of decreasing the number of randomly selected features at each split is that it significantly reduces the correlation between the individual trees in the forest.
Reduces correlation.
Well, if all trees were allowed to consider the exact same best features at every split, they would tend to make very similar decisions and thus end up being highly correlated with each other. By forcing each tree to consider only a random subset of features at each split, you encourage more diverse, less correlated trees.
More diverse trees.
Yes, and this increased diversity among the individual learners, when aggregated, leads to an even more robust and accurate ensemble that is less prone to overfitting and performs exceptionally well on unseen data. It makes the forest stronger.
If bagging primarily focuses on reducing variance, are there ensemble techniques that focus on reducing bias, perhaps by learning from the mistakes of previous models? Fixing the core assumptions.
Absolutely. That's the primary domain of boosting, with algorithms like AdaBoost and gradient boosting being prominent examples.
Boosting. Okay.
Unlike bagging, boosting trains models sequentially, not in parallel. Each new model in the sequence doesn't just get a fresh sample. It specifically focuses its attention on the errors made by the previous models in the ensemble.
Focuses on the errors.
Yes. It essentially boosts the importance of data points that were misclassified or poorly predicted by its predecessors, thereby learning from the mistakes of the earlier models.
So the models are dependent on each other, building upon each other's performance. And what kind of models does boosting typically use? Big, complex ones.
Exactly. They are sequential and highly dependent. And interestingly, boosting typically employs weak learners models that perform only slightly better than random guessing.
Weak learners.
Yeah.
Like not very good models.
Individually, yes. A very common weak learner used in boosting is a decision stump, which is essentially a decision tree with only a single split. Just one question.
A one-split tree. Okay. How does it work?
The algorithm works by assigning weights to each training data point. Initially, all points might have equal weights. After a weak model is trained, the weights of the incorrectly classified points are increased, while the weights of correctly classified points are decreased.
Pay more attention to the hard ones.
Precisely. This clever weighting mechanism ensures that the next weak learner in the sequence pays significantly more attention to the examples that were harder to classify, continuously trying to correct the ensemble's previous errors.
And how do all these sequentially trained weak models combine for a final prediction? Is it just a simple sum or average?
No, it's a weighted combination. The final prediction from a boosting ensemble is a weighted sum of the predictions from all the individual models. Crucially, models that perform better, i.e. those that have lower error rates on the weighted data they were trained on, are assigned higher weights in the final ensemble.
Better models get a bigger say.
Exactly. They contribute more significantly to the ultimate decision. This ensures that the more reliable weak learners have a greater influence. The primary benefit of boosting is its remarkable ability to reduce bias and achieve very high accuracy, often transforming a sequence of seemingly simple, individually weak learners into an extraordinarily powerful and precise predictor.
So far, we've largely focused on situations where we either want to predict a number or classify data into predefined categories. We have labels. But what if we don't have any labels for our data at all? What if we just have a pile of information, say a collection of customer reviews or a huge database of images, and we simply want to find natural groupings, discover hidden patterns, or understand the inherent structure within it without any preconceived notions? Unsupervised learning.
This is where we step squarely into the fascinating and often exploratory realm of unsupervised learning. In this paradigm, the goal isn't prediction based on labels, but rather to uncover intrinsic structures and relationships within the data entirely without prior knowledge of categories or classes. We're letting the data speak for itself, revealing its own underlying organization.
And where do we typically begin when we're trying to group data without any labels to find these natural clusters? What's the go-to method?
The most common and widely recognized starting point is k-means clustering, often implemented through what's known as Lloyd's algorithm.
K-means.
The core objective of k-means is elegantly simple: to partition your data points into a pre-specified number of mellitor-distinct clusters. Each data point is then assigned to the cluster whose mean, or centroid, is geographically closest to it in the multidimensional feature space.
How does this algorithm actually go about finding these clusters in practice? What are the steps?
It's an iterative two-step dance that repeats until stability is reached. 1. Initialization. First, you explicitly specify the number of clusters you want to find, which is your dollars. Then you randomly assign initial cluster centers, or centroids, to kick off the process. Maybe just pick k random data points as the first centers.
Okay, pick K and pick starting points.
2. Assignment step. In this step, every single data point in your dataset is assigned to the nearest of these currently existing cluster centers. Just calculate distances and find the minimum.
Assign everything to its closest center.
3. Update step. Once all points are assigned, you recompute the cluster centers. Each new centroid is simply the mean average position of all the data points that have been assigned to its cluster in the previous step.
Move the center to the middle of its points.
Exactly. 4. Iteration. You then repeat steps 2 and 3, reassigning points to the new nearest centers, and then recomputing the means until the cluster assignments no longer change. This signifies that the algorithm has converged to a stable configuration.
Assign update, until it settles down.
And what's a mathematical objective function that k-means is trying to minimize during this iterative process? What's it optimizing?
The objective function in k-means is the sum of the squared distances of each data point to its assigned cluster mean. This value essentially quantifies how compact or tight the clusters are. Lower is better.
Sum of squared distances to the center.
Okay, what's quite satisfying about Lloyd's algorithm is that this objective function's value strictly reduces with each iteration. A point will only ever switch clusters if it finds a new centroid that is closer, which by definition reduces its square distance to a centroid, thereby decreasing the overall sum of square distances. The algorithm is guaranteed to converge to a local minimum of this objective function. So these clusters must have specific boundaries, right? What do those boundaries look like in the feature space? Are they circles?
Yes, they have boundaries, but they're not necessarily circles. The boundaries that separate any two clusters in k-means are always defined by the perpendicular bisectors of the line segment joining their respective means.
Perpendicular bisectors, straight lines or planes.
Exactly. If you have more than two clusters, these individual bisecting lines or hyperplanes collectively form what's known as a Voronoi diagram. Each cluster occupies a region of the space where every point within that region is closer to that cluster's centroid than to any other centroid. This creates geometrically precise, piecewise linear boundaries.
Voronoi diagram.
Okay.
We've discussed how other algorithms like perceptron can be sensitive to their starting point. Is k-means sensitive to how you initialize it too? Does that first random assignment matter a lot?
It's extremely sensitive to the initial placement of those cluster centers. A poor initialization can lead k-means to converge to a local minimum of the objective function, rather than the global minimum.
Local minimum. So, a suboptimal solution.
Yes, this means you might end up with suboptimal or unnatural clusters simply because of where you started the process. To mitigate this common pitfall, a smart initialization strategy called k-means plus plus is often used.
K-means plus plus O. How is it smarter?
Instead of pure random assignment for all centroids, k-means plus plus chooses the first center randomly, but then subsequent centers are chosen probabilistically, favoring data points that are farther away from any already chosen existing cluster centers.
Try to spread out the initial center.
Exactly. This strategic seeding significantly improves the chances of reaching a better, more globally optimal clustering solution.
And how about outliers in the data? Are they a problem for K-means like they are for some other methods?
Yes, k-means is quite sensitive to outliers, and they can be a significant issue. Since its core operations involve computing cluster means and relying on Euclidean distances, an outlying data point, a point far from the main group, can disproportionately skew the position of a cluster centroid, pulling it away from the true center of the main body of data points it's supposed to represent.
So one weird point can mess up a whole cluster center.
It can. This can lead to unnatural cluster shapes or even cause an outlier to form its own small, isolated cluster. Additionally, choosing an appropriate dollar, the number of clusters, is absolutely crucial.
Choosing K, always a challenge.
It is. If dollars is too small, you might miss natural distinct groupings within your data. Conversely, if dollars is too large, you might create trivial or artificial clusters. For example, if dollars equals the number of data points, each point simply becomes its own cluster, and the objective function, of course, drops to 0, which is meaningless. Finding that meaningful dollars is a separate, often challenging problem in unsupervised learning.
K-means sounds excellent for finding distinct, spherical-ish clusters. But what if our clusters aren't perfectly round, or they overlap significantly, or we want a more sophisticated probabilistic understanding of the underlying groups in our data, a softer assignment than just in or out?
If we connect this to the bigger picture, this is where Gaussian mixture models, GMMs, become incredibly powerful and offer a more nuanced approach.
GMMs.
Instead of assuming crisp, hard assignments of data points to clusters, like k-means does, GMMs model data as being generated from a mixture of several Gaussian or normal distributions. Each Gaussian component essentially represents a different cluster.
So each cluster is a bell curve.
Essentially, yes, though it can be a multidimensional bell curve and ellipsoid. A key difference is that GMMs provide a probabilistic membership for each data point to each cluster. So a point isn't just in cluster A, it might have a 70% probability of being in cluster A and a 30% probability of being in cluster B.
Probabilistic assignment. That sounds more flexible. How do we find the parameters of these Gaussians?
We use the expectation maximization, EM algorithm. It's used to estimate the parameters of these underlying Gaussian components. Their mixture probabilities, how likely you are to draw from each component, their means, the center of each component, and their variances or covariance matrices, the spread and shape of each component.
Expectation maximization, EM. So it's not just a hard assignment, but a soft probabilistic one. How does this EM algorithm actually work to find these parameters? It sounds quite sophisticated.
The EM algorithm is an iterative optimization method that gracefully alternates between two main steps until a stable solution is found.
2 steps. Okay. Expectation and maximization.
Exactly. First, there's the E step, or expectation step. In this phase, given the current estimates of your model's parameters, the means, variances, and mixture probabilities of each Gaussian component, you compute the responsibilities, often denoted as lambda.
Responsibilities.
These are the posterior probabilities that each data point Vessier belongs to each mixture component later. This calculation typically involves using Bayes' rule. Essentially, for every data point, you ask, based on how I currently understand my clusters, what's the probability that this particular data point was generated by this specific Gaussian cluster versus any of the others? You calculate that probability for every point in every cluster.
So figure out how much each point likely belongs to each cluster. And then once we have those probabilistic responsibilities, what happens in the maximization step?
That's the M step, or maximization step. Here, you take the responsibilities calculated in the E step, and you use them as weights to update the model's parameters, the means, variances, and mixture probabilities for each Gaussian component to maximize the overall log likelihood of the data.
Use the responsibilities as weights to update the clusters.
Precisely. So if a data point has a high responsibility for belonging to a certain cluster, it will contribute more significantly to recalculating that cluster's mean and variance, essentially pulling that cluster's parameters closer to itself, weighted by its responsibility.
And then repeat. EM, EM.
Yes, you repeat these E and M steps iteratively. With each complete cycle, the overall log likelihood of your observed data consistently increases, guiding the model towards a better and better fit to the underlying data distribution.
So we're talking about likelihood functions again, similar to what we saw in regression and logistic regression,
Yeah.
just adapted for different types of distributions.
Exactly. The concept of likelihood is fundamental across many statistical models. We calculate likelihood for different distributions depending on the nature of our features. For example, Bernoulli for binary data, like a coin flip, Gaussian for continuous numerical data, like height or temperature, or Poisson for count data, like the number of events in a time period.
And why log likelihood?
To handle the multiplication of many potentially small probabilities, which can lead to numerical underflow, we almost always work with the log likelihood for numerical stability. Maximizing the log likelihood is equivalent to maximizing the likelihood itself, but it transforms products into sums, making computations much more manageable and stable.
And choosing the number of mixtures
Mhm.
for GMMs must be just as important as choosing dollars for k-means, right? How do we approach that? Still tricky.
It is, absolutely. The number of mixtures in a GMM should ideally reflect the underlying distinct distributions you believe are present in your data. It's a critical hyperparameter.
So you need some domain knowledge or exploration.
Often, yes. For example, if you're analyzing a data set of human heights and you suspect your population is a mix of adults and children, you might initially hypothesize two Gaussian components. If you then find your data truly represents a population that has, say, a significant subgroup of professional basketball players, you might then consider three or more components. Finding the right dollars often involves looking at statistical criteria like the Bayesian Information Criterion, BIC, or a Akaike Information Criterion, AIC.
DIC and AIC. Heard of those?
Yes, these criteria penalize models for increasing complexity, helping you balance fit with model parsimony. They help you find a K that fits well without being overly complex.
And similar to k-means, can the EM algorithm for GMMs also get stuck in local optima depending on where you start? Is initialization still a problem?
Yes, that's a key challenge, very much like k-means. The EM algorithm for GMMs can be sensitive to its initialization and may converge to a local optimum rather than the global optimum of the likelihood function.
Darn local optima.
They're everywhere in optimization. If your initial guesses for the means and variances of your Gaussian components are significantly far from the true underlying means, they can create barriers that prevent the algorithm from finding the best possible fit. A common practice to mitigate this is to run the EM algorithm multiple times with different random initializations and then select the solution that yields the highest log likelihood.
Run it many times, pick the best one.
Exactly. This increases the chance of finding a good, robust clustering.
We've taken a truly comprehensive tour through the fascinating world of data and machine learning, from the elegant simplicity of understanding data dimensions with vector projections,
All the way back to the start.
all the way to the intricate dance of sophisticated algorithms like support vector machines and Gaussian mixture models. We've seen how mastering these fundamental building blocks and techniques allows us to build remarkably powerful predictive models, uncover elusive hidden structures in unlabeled data, and confidently navigate the vast, often overwhelming oceans of digital information.
If we connect this to the bigger picture, what stands out most profoundly is the deep, consistent mathematical foundation that underpins every single technique we've discussed.
It all comes back to math.
It really does. From understanding data spread with PCA to making nuanced, highly accurate predictions with ensemble methods. It's all built on logic and numbers. And, as these models become increasingly complex, powerful, and integrated into every facet of our lives, this raises an important question.
Which is?
What new challenges, not just technical, but also in terms of interpreting what these models are actually doing and why the ethical side too will arise from their unparalleled ability to speak the language of data with such fluency.
Interpretability and ethics.
Yeah.
Yeah.
It's definitely something to mull over as you encounter more and more AI in your daily life and consider what it truly means for the insights we gain and the decisions we let these systems make.